The usual rules of linearity apply for differentiation. The derivative of a sum is the sum of derivatives. That's no different. So if you have derivative of a sum of forms, you can just differentiate them individually and add the results. No surprise there. Also, again, you can treat functions as constants, if you will. Actually, no, not this time. Because if you're differentiating a product of forms, then there's a product rule that applies. But it's not exactly the same as the product rule that you are accustomed to, because it has to take into account that when you multiply forms, it's not commutative, it's anti-commutative. So that rule crops up again. So suppose you have a product of forms that you're differentiating. So the first thing you do, it starts out like the standard product rule. You differentiate the first one, omega, wedge product with n, eta rather. Now, the regular product rule would suggest that what you do is you have omega wedge d eta. And that's almost right, but you have to add this, minus 1 to the k times L, where omega is order k.
I don't think L's in the notes.
What?
Is it not?
Oh, shoot. Yeah. Oh, wait, you know what?
Huh?
Actually, I think it is really supposed to be k. Just k in this case. Great. I don't remember.
So that'd be like making points there, right?
Shall we consult someone?
Well, it's not in Stewart. It's in Marsden. But I also have an example down here.
Do you want a book?
Oh, yes. That'll.
No,
but since the student's supposed to be more proficient, it is you go even longer.
We're learning from your mistakes.
It's been 22 years. So, all right.
I'll shoot 5.
Okay. Yeah, so unlike the k of it appears as a wedge product, it's just minus 1 to the k here. Now what that means is, if this is a zero form, if it's just a function, then the standard product rule would apply. And then finally, one that simplifies things quite a bit. Anytime you have a basic one form, like a dx, the derivative of that, 0. Same thing for dy, dz. So in other words, d squared, look at it this way, d squared is always 0. You can't apply it twice to the same basic entity. All right. Okay, actually, all right. This could work out perfectly, because then I'll just get through some examples involving the operations, and then time will be up. And then on Thursday, this will be about how these are actually applied to take all those 5 theorems and condense them into one. And that will give 2 days for all of us, including me, apparently, to forget all this. Couldn't have planned it better if I tried. Okay, so again, there are certain rules that are more important than others to keep in mind. This is pretty standard here, just applying it through to the function, differentiate with respect to all its variables, linearity, whatever. Keeping in mind product rule, in case you have to flip the sign, and then this rule is going to come up a lot, that d of dx, d of dy, etc. is 0. All right, so now let's do an example of that, of differentiating a 2 form, which will give us a 3 form. All right, so x squared, y cubed, z to the 4th, dx dy. So this is a 2 form, and we're going to differentiate it. So the way this is going to work is here we have a wedge product of this function with this. So we're going to have the derivative x squared y cubed z to the 4th, wedge product with dx dy, plus, this is a 0 form, this is a 2 form, so we can have minus 1 to the 0, so no sign change in this case. If ever going to have x squared y cubed z to the 4th times the derivative of dx dy. So that's how we start off. This is the product rule. Okay. So now, if we focus on this one, we're going to have this becomes x squared y cubed z to the 4th with respect to x dx plus x cubed squared y cubed z to the 4th with respect to y dy plus x squared y cubed z to the 4th dz, partial respect to z, and then wedge product with dz, and then all of that wedge product with dx dy. Now over here, we're going to have plus the function undifferentiated, and now you're going to compute the derivative of this. Well, this is going to be d dx dy minus d dy minus dx d dy. Because these are 1 forms, this time by the second part of product rule there is going to be a sign change. But what's this going to turn out to be?
0.
Yeah, both terms, because we have a d of dx, this is 0, and your d dy, also 0. So that's the nice thing is really, you just got to worry about the function. Computing its derivative to get a 1 form and handling this wedge product. Everything else is going to go away. So that saves you a lot of work. So now what we're going to do, here we have 3 terms. So we're going to distribute this wedge product across these 3 terms. So we're going to have, let's do a differentiation here. We have 2x y cubed z to the 4th dx dy plus, here we have 3x squared y squared z to the 4th dy dx dy plus 4x squared y cubed z cubed dz dx dy. But what happens to this?
0.
This first term is 0 because we have the 2 dx's gone.
0.
0 again. dy dy. Bless you. Don't bother interchanging to put them together. It doesn't matter whether they're really together or not. They're in the same product. It's going to end up being 0. So that's gone. This is the only one that's left. So if we want to put the z at the end, just for convention's sake, we need to do 2 flips. Bless you.
Here's that. That's not even going to change the sign. It's
Just
just
eventually, exactly, because you do 2 flips. In the end, there's no sign change. So it's 4x squared y cubed z cubed dx dy dz. So notice, because we had a dx dy already sitting here, only the derivative of this with respect to z, the variable that's not included in here, ends up making any contribution. So what if, instead of this 2 form, suppose you started with a 3 form, and you have to compute its derivative.